Hello everyone. Today we have Prajakta from Einstein, hosting a talk on gravitational lensing and some big explosions in space. So let's welcome her with a round of applause.
Hello, I'm Prajakta. I'm a scientific physics major and have been working on observational cosmology since my last summer project, and I'll be continuing the work in this coming summer as well. So in this talk, in my work I specifically focus on gravitationally lensed systems of Type Ia Supernovae. So if you can see this particular image, this is a very classic example. It's supernova red star, named after the person red star who basically gave the first mathematical description of gravitational lensing. So to honor him, this was one of the very first gravitationally lensed Type Ia supernova systems, and they named it after the person who gave the first mathematical description of gravitational lensing. So this is a very classic example. I can also tell you more about this if anyone has a question, but if you want to read, this is a very fascinating case, and if you want to read more about this, then I have written an article in the blog of astronomical, so you can go. It is a very fascinating case, so I will say that you guys should go and read that article. I can also but in this talk I will be talking about, I will be sort of introducing or giving a mathematical overview of the theory of gravitational lensing. How, when we say that we are studying a system of gravitationally lensed case, what we mean, like what parameters do we study, and how they are mathematically described. So that is what I will be talking about in the first part. Then I will come to the most powerful explosions part, which is the supernovae. I will talk about a very briefly introduction to what are supernovae and what are this particular type or class of supernovae, that is Type Ia Supernovae, which I have been working on. And in the second part, I will combine the lensing and the supernovae part, and I will talk why we should study these systems, why we should study Type Ia Supernovae, and why, in particular, what I am doing, why we should study the gravitationally lensed Type Ia supernova systems. What are the implications? So this part will be focused on cosmological point of view. I will discuss what are the cosmological implications or what inferences on cosmological scales we can find from studying this particular class of objects, gravitationally lensed Type Ia supernova. So to start, this is a very classic image. All of you must have seen this image from, it's a Hubble deep space patch of the sky taken by JWST. It's one of the first releases by JWST, and this is sometimes called as the zoo of galaxies. You can see so many galaxies, all of these galaxies you can see, and it's also a very standing out picture showing gravitationally lensed galaxy. You can see all of these arcs that you see are all of them are gravitationally lensed galaxies, and some of them might be some other astronomical objects like quasars, for example, or stars. Some massive stars also get gravitationally lensed. And so, taking this picture as a starting point, we will dive into the phenomenon of gravitational lensing. Let's just consider that we are here. We are observing some particular object which sits over here. This is our source, and this is us sitting on Earth, or some observatory, ground-based observatory, or some observatory rotating around the Earth in space. And we are observing the source. In normal cases, what we will expect is the light from the source comes in a straight line. It's not a very straight line, but just assume it's a straight line. And light from the source comes to us in a straight line. It follows a straight line path, and we see the source. Let's draw x-axis and consider that the angular position of the source with respect to some horizontal axis is beta. Okay? Now we introduce a lens. What will happen if there is like a very massive body which has its huge gravitational potential, which sits between the source and the observer. This is our lens. In that case, this is a very simplified picture, obviously, but as it turns out, it works for many, most of the cases of gravitational lens systems. And so we continue with this simplified picture, and we just assume that we say that obviously the gravitational potential of the lens will cause the light from source to bend before coming to us. And we assume a very simplified version and take a kink here instead of continuous bending. Under subtle approximations which hold true in most of the astronomical systems, and we will say that the source is bending while coming to, before coming to us, and it reaches to us at this particular angle, which at particular angle theta. And we have seen this case while studying optics, and we say that actual optical lens is present convex or concave, and then we draw similar figures. And this is also a reason why it's called, phenomenon is called lensing, gravitational lensing, because it happens because of the gravitational potential. And we see the source, we see the image of the source here at angle theta. And the difference between the angle, we call it as alpha of theta. And from the very simple geometrical construction, you can reach the equation that the angular position of the source is equal to the angular position of the image minus this particular small angle, which we call alpha of theta. Okay, all of these are vectors. Okay, and this angle that the image makes with the source, we call it the angle of deflection, and we denote it by alpha of zeta. Zeta is the impact parameter of the light ray. So for this is the impact parameter is the word you heard by studying collisions of systems, or for example in Rutherford experiment. And the same concept is applied in a very simplified manner here, that the path that the light takes has some impact parameter from the center of the lens, and we take that as a zeta. And this angle, the deflection angle, depends on how close. For example, if that ray passes at a smaller impact parameter, say from here, it will get more deflected simply because it's closer to the object, and the gravitational potential bends the light ray more, it distorts the light ray more. So this angular deflection is a function of the impact parameter. And this is the exact figure that we see here. This is the Earth observer, this is the lens, this is the source. This is the angle between, this is the angular position of the source, theta, and this is the angular position of the image, theta. And this angle that I depicted here, and this is the angle of deflection. Okay. The distance from the observer to the lens, we take it as dv. The distance from lens to source, we take as dds, and the distance from observer to source, we take as ds. It's a simple, very simple geometrical construction. And we saw this particular equation, which just comes from this geometrical construction, and this equation is called as the lens equation. Now, focus on this lens equation. This parameter beta is in the it's not. So this parameter beta, can you see the cursor? Okay, the parameter beta falls in the source plane, right? The parameter beta gives the position of the source, and we say that it falls in the source plane. And similarly, the parameter theta falls in the image plane because it gives the angular position of the image. What this lens equation does is it gives a transformation from source plane to the lens plane. If we know the angular position of the source, we can go to image plane, and if we know the angular position of the image, then we can go to source plane. If we know this parameter alpha of theta. So we need to know this parameter. That is why I have written the next step of the line, the next equation, which is what is alpha of theta. The alpha of theta is simply dds, the distance from lens to source, upon ds, which is distance from Earth to source. The distance from lens to source upon distance from Earth to source into this factor, this deflection angle, right? Okay. And this deflection parameter, as I said, from Einstein's GR, the angle of deflection can be given as Gm upon c square into the impact parameter. This is the mass of the lens that deflects the body, or that deflects the light ray, which is the mass of this lens. And the impact parameter, as I described, is the impact parameter of the light from the lens, from the mass. So this is and then this equation is again simplified in terms of sigma, which is the surface density. If we have, for example, the lens, our lens is a galaxy cluster. We might not have uniformly distributed galaxy cluster because there will be patches, there will be galaxies which will act as patches. And the mass is not uniformly distributed. So instead of taking whole mass, we turn this as a function of the surface mass distribution, how the mass is distributed over our lens. And this integral is the parameters, both the parameters of mass and the impact parameter, and we get this thing. And now, as we discussed before, we need to find what is alpha of theta. And this equation tells us that it depends on the surface mass density of the lens and the impact parameter. How distant, what is the distance between the path of light and our body or our lens. And surface density we will know because there are a lot of surveys that have mapped our sky, entire sky, and figured out the masses of different bodies. And we should have this information from observational data that we have. And now focus how I have rearranged the same equation, the alpha of theta equation. I have modified it to the smaller looking equation, and this might look very unmotivated. Why do we need to rearrange, and why do we need to bring this additional parameter of kappa? Kappa of theta is the new parameter that we have eliminated some parameters and we have included the parameter kappa of theta. Now it might seem very unmotivated. This is just jugglery of equations. Why do we need to modify these equations? That is because kappa of theta is something that can give us interpretations in terms of things that we can observe. So we have a theory and we need to test if this theory works. The simplest way of testing this is we find the implications that can be observed. So we write down the theory and we lie down some implications and we say can these implications be observed? And then if they can be observed, you observe them and the observations refute or accept the theory. So that is how it works. And kappa is defined as the surface mass density of the lens divided by the critical surface mass density, where the critical surface mass density is given by this formula. Now notice here that these are just constants, so they will stay constants, but the surface mass density, the critical surface mass density, depends on these factors which are the distances, and these distances will be very specific to each lensing system. So the critical mass density, what I am trying to say is the critical mass density will change as our lensing system changes. If we have one lensing system, then these distances will be different and the critical surface mass density will be different, and that will be different for a different system of lens schemes. Okay. And so this kappa is given as the sigma of our system on the critical sigma of our system. And I'll come to, so keep these two things in mind. First, the lens equation gives the transformation from the source plane and image plane, and the second thing is kappa, and we'll see why. Okay. And these are the physical interpretations that is lensing, the last slide is basically. First is if the lens equation has more than one solution for a single value of beta. Okay, imagine you are trying to feed in the source position in the lens equation, the theta position. You know that certain object is there and you want to model how the lensing event will be for that particular source. What you will do is you will take the position of that source and you will feed it into the lens equation and design some lens with some certain particular surface mass density and feed that alpha of theta. And you will get, what you will get is the theta positions, which are the image positions, and you will be able to tell how the images, where the images will be located, the positions of the images. Now, if the lens equation has more than one solution for a single value of beta, if you feed in the beta and if you get multiple theta values, what that means is your images will be more than one. You will get more than one images at different locations because the thetas are different and thetas are more than one. So the source is getting imaged at more than one location, and that is the case of multiply image lensing event. You might have seen those pictures where one source is getting multiply imaged. For example, the first ever case of gravitational lens system was a quasar, which was observed to be one quasar was imaged into four images, which were arranged in shape of cross. That phenomenon is called as Einstein cross, something like this. Very, very close by, but resolved four images. So this is the case of multiple. This is how you get multiple image sources. And this condition is satisfied if a mass distribution is kappa greater than 1. So again, going back to the previous slide, if your kappa is greater than 1, that is your surface mass density of the lens is greater than the critical surface mass density of your system, then this condition gets satisfied and you get the case of multiple image source. So you can predict if you know your lens distribution, lens mass distribution, then you can predict if you only get one image or you get more than one images. Okay, that is why we noted the kappa parameter, because it predicts something that you can observe. And then the third thing is this inversion of lens equation to obtain image positions theta from source positions beta. You are feeding in beta and you are finding theta. You are feeding in the source position and finding the image positions. Can be carried out analytically only for very simple mass models of the cases. As number of images theta per given source beta is not known a priori, the numerical inversion is a non-trivial. So you are trying to solve this lens equation, and it might look very simple, but the integration involved there, you cannot solve it numerically for a general case, any general mass distribution. It is not exactly solvable even numerically. You cannot solve it analytically, but you cannot also solve that source position thing even numerically. But it gets easy if you know what are the numbers of images that I am going to get. So first thing is you can predict from kappa is if you are going to get one image or more than one images. But it becomes even more easy if the number of images is more than one, and if you can predict how many exact number of images. Is it 3? Is it 4? Is it 2? Then the inversion, then that lens equation, solving the lens equation analytically becomes much more simple. And that also we do it in simple mass models of the lens. So I will not go to what is this, but we just model different types of lens and try to solve that equation. But the point to keep in mind here is it gets easy if you know a priori what is the exact number of images that you are going to get. Okay, so this is the takeaway from this slide. Okay, moving forward, these are the important parameters that we study in lensing. Mathematical equations. So I am combining them. First is magnification, and second is distortion. Okay, yeah. So in this particular image, this is the overview of your system that you are studying, and this is what you actually see. This is a simulation. I think they made it for supposed to represent JWST, and they made it for JWST. So this is a galaxy cluster here, which is acting as your lens, and this is something that the source basically that is getting lens, and this is the actual thing that we see. Here actually, because this is the galaxy cluster, you can see the original galaxy cluster, and you can see the sources that have been lensed here. They are very faint, but you can see, for example, this one. You can see the arc, right? And so these, you can clearly see the distortion here. You can see that the galaxy, you know the general shape of galaxies, and you know that they are not supposed to look like this. They are supposed to look like arcs. And there is a very clear case of, like, you can see how it distorts, how it gets distorted, and it also gets magnified. And now what happens, I'll explain what exactly happens in the magnification, but the nice thing about gravitational lensing is that because the magnification is one of the parameters, you can see more back in time or more back in space than you can usually see. For example, this is your observatory, and imagine the case where you can only see till the lens. Like every telescope has its own limitation till what distance it can see, right? And imagine that the telescope, this telescope can only see till the lens, where the lens is, that only that much distance it can probe. But now because it cannot obviously go back there where the source is, it cannot observe the source in general conditions. But now because the gravitational lensing is happening in the system, and because magnification is one of the parameters of gravitational lensing, or one of the implications of gravitational lensing, we can expect that the background source in one of the images will get magnified. And because it is getting magnified, because the brightness of the object is changing, it's getting multiplied, or like getting more basically, you can imagine how we can still be able to see that background source just because the gravitational lensing is happening. And so this is going to play a very important role, because gravitational lensing has been used to look back in time. I mean, apart from everything else, like the lensing, original lensing implications, one of the major use that astronomers have done of gravitational lensing is looking more and more back in time, so that you can figure out what was there before. Like, you can't see there, but if a system at this distance is getting gravitationally lensed, it gives you an aid to look there. And one of the major things in telescope buildings, or why JWST was like, why people had so many hopes from JWST, is because you could see back in time and you could see what is going on there, what happened back in time, and what are the implications of it in today's or in the future of our universe. So that is a good thing. And then the third parameter is time delay. So this is again an example, classic example of quasar gravitational lensing. And you can see these are the spectra. This is the relative image flux, and this is the time. So it just gives how the relative flux of a quasar is changing with respect to time. And you can see they have mapped these particular epochs, and they have studied the spectra, and these particular epochs are those epochs that are same. I mean, this particular epoch here corresponds to this epoch, and this epoch, and this epoch. So all these spectra, like these points correspond to same point, but there is a time delay. There is a clear shift in time, which you can see, right? And this is a parameter of time delay. Here you can see the images as well. This A image came on day 127. This B image came on day 95. The C image, the B is the first image that popped out, then A popped up, then C popped up, and then D popped up, right? And you can see how the shift in time is happening here in the spectra basically. So that is the third parameter of time delay. Now we'll go into the details of this. Magnification and distortion, these two parameters are governed by the same mathematical equation, which is the magnification matrix. Now I talked about frames, or like going from image plane to source plane, right? And you can look at this as a coordinate transformation, or like frame transformation. That lens equation gives the transformation. And if you know, for any general case of coordinate transformation, say for example, if you are going from xy coordinate to Cartesian coordinate to spherical coordinate, you get this one particular quantity of Jacobian, which gives basically how. So for example, you are measuring a volume of a sphere in one particular coordinate system, and you are measuring the same volume of same sphere in second frame, and you will see that because of the frame changes, the value that you will get for the volume will change, just because of the frame transfer. The object is same, you are calculating the volume by same method, but because your coordinate system has changed, it will either undergo expansion, or something will happen to it, and that change is what the Jacobian gives you, Jacobian of the coordinate transformation. And the same general rule applies here as well. The magnification of each image is related to the Jacobian of the transformation equation. The transformation equation was beta is equal to theta minus alpha. And this magnification matrix will be given by del theta by del theta, which is source position, the derivative of source position, which is image position with respect to source position. And this magnification matrix, if you had to lay out in the form of parameters, it will be given by this. I will not go into what is gamma, what is kappa, what is gamma 2, and what is psi, but because I have not introduced the format potential. But if you can see, just focus, take my word and say that this is the magnification matrix. You can clearly see that you can separate this magnification matrix into two matrices, which is one of them is just diagonal and the other one has off diagonal elements. Right? Now the first matrix, which is it just has diagonal elements, what it will do is it will give symmetric distortion. The whole thing gives the distortion, but the first matrix will give symmetric distortion in the sense that if you have a source which is perfect sphere, which will be projected at us as a circle, we will see it as a circle, then the first matrix will give you symmetric distortion in the sense that just the size of it will increase. And when I say size or radius, I mean the brightness, right? And it is just like the circular source or like the circular brightness distribution will just increase in terms of magnification. It will just symmetrically be magnified. Whereas the second matrix, which has off diagonal terms, non-zero off diagonal terms, it will give you shear. It will not be symmetric. So, for example, if you have a circular mass distribution, it can transform into an ellipse. So, this is what is shown here. So, this is your brightness distribution, which assume it's circular, and this just gives you symmetric magnification or symmetric shear, and this thing, the ellipse, is what you can expect from the second magnification matrix. So, this is how you get magnification and shear, right? Now, from the third slide, I think I had mentioned that the inversion of the lens equation it gets easy if you know what are going to be the number of images that you get, right? And this is how you predict the multiplicity. The number of images you call multiplicity, and okay, so this is your source plane. This is your source. The source lies somewhere in the center of this image, and similar for that figure. But this item is in the source plane, and this item is in the image plane. In very simple words, these are your sources. If these are your source positions, then those will be your image positions. So you can see, and these are called caustics, and the caustics. This is also a very general case. If you have studied Jacobian, you can set the determinant of A matrix that I gave, which was the Jacobian transformation. If you set that determinant to be 0, you will get these curves. And this is a very general thing which we apply in gravitational lensing. And so, for example, if you can also understand this intuitively in the sense that if your source is very close to the lens. Okay, I said something wrong. The center of the images should be lens, not the source. These are the sources, and the center is the lens. Okay, so this is your lens, and these are your sources. So if your source is very close, in the sense that your lens is here, and your lens is arranged in a line of sight. By close, I mean the source and the lens are arranged in line of sight with each other. This is off line of sight, and this is line of sight, right? So if your source is in the line of sight, very line of sight to the lens, then you will see 5 images which are like that red dot, the red dot which is very close in the inner circle, and that very distorted arc. And as you move away from your lens, or as you move off the center of line of sight from your lens, the number of the images firstly decreases. You can see the green also has 5 images, sorry, and this magenta images are 3. If you cross the curve, the number of images will decrease by plus or minus 2, or like it will change by plus or minus 2. If you come inside, it will increase by 2. If you go outside, it will decrease by 2. And very far away from the lens, you will only see one source, because the source is 1 and you will see it as it is. So that is 1 image, if you consider in terms of images. And as you move inside the caustics, the number will increase by 2. Okay? And you can also see the distortion of this red image is very much compared to other images. And that is because it is very close. If you have a very rare case where your lens and your source absolutely are in line of sight, they are very much in line of sight, then you will see an entire ring, and that is the case of Einstein ring. And these cases are very rare, because you can imagine what is the probability of 3 objects aligning in the same line. But we have observed these cases, and you actually see the entire ring, and that is how the distortion distortion works. Okay. And coming to the third parameter, time delay. This is relatively easier. You get time delay because of so when I mean time delay, I mean the time of popping out the images in simpler words. What time one image came out, what time the second image came out at, what time the third image came out at. And this time delay between the appearance of images arises because of two factors. One is the geometrical time delay. As you can imagine, the light is taking different paths. So this is one of the paths. This light might take other path, light might take other path, and because the impact parameter is changing, the reflection angle will change, and because the reflection angle is changing, the path length that each light ray will take or each bunch of light ray will take will be different. And because the path length is different, it will take different time to come to us or reach us. That is the geometrical time delay, which is given by this first equation before plus. And the second point you get is the gravitational time delay. It comes because the lens has very high gravitational potential, and the light ray coming to us simply simply sees the slowing down because of the gravitational potential. Because the space around the lens will get curved, and it will simply be like a dip. I don't know how to explain this in a better manner, but this will be seen by the gravitational time delay. Okay, and these two parameters add to give the total time delay. So you have to remember this equation. dt depends on the three distances. It depends on the speed of light. It depends on the redshift of the lens. What redshift, what distance the lens is at from us. This is the redshift of the lens. Okay, not the source. And this is something that I have not introduced, but it's okay. I will not talk about this, but you can ask me about it if you want. But it's not a mystique parameter. It's just I'm not talking about it because I'm not introduced it in the talk. But this is how it depends on the sea, it depends on the distances, and it depends on the speed of light. And something it's a difference in the Fermat potentials, which will not play a lot of major role in the coming discussion. So this was the entire thing that I wanted to say about the lensing. And okay, and now we are coming to the supernova part. And this will be a short discussion. Supernova, most of you might have heard, it either is a explosion of a dying star. Each star at the end of its life undergoes a supernova explosion, or it can also come from when a white dwarf star is in a binary system with some other star, and they are rotating with each other, and at some point they come so close to each other that the white dwarf star, because it's too dense and explosive, it starts eating the mass from the other star. And at certain point, you know that the white dwarf stars have this limit of mass called Chandrasekhar limit. So while eating the mass from the other star, if the white dwarf star crosses that mass limit, it becomes more massive than 1.4 solar masses, which is the Chandrasekhar mass limit, then it booms, it explodes. It cannot take the electron pressure, cannot take that much mass, and it just explodes as a supernova. And that supernova is what we call as Type Ia Supernovae. All the supernovae are classified as different types according to based on their light curves. Each supernova follows a very specific type of, not each supernova, but each type of supernova have distinct types of light curves, how their flux changes with time. And light curve is just the flux upon time versus time graph. And they're classified according to their light curves and their absorption lengths, the spectra, how their spectrums change. Okay. Yeah, so I talk little more about the light curves of Type Ia Supernovae. Type Ia Supernovae in optical follow this very generic type of light curve. They explode, the supernova goes off. They climb this flux curve and they reach this peak intensity or peak brightness, and then the brightness just falls down with respect to time. Okay, and the very astonishing fact is that if you look at a Type Ia supernova in any part of the sky, in any direction, equation at any distance, you will always get this type of curve, and the peak flux that you get is always the same. It's some 10 to the power 46 brightness units, okay? And this is always the same, standard, and that is why it's called the standardized canvas. If you attended Kaushik's talk in the Talk of Tuesdays series, then he talked about this, and we use this fact that the Type Ia Supernovae standardized candle extensively to measure distances and all sorts of things. So I'll come to that. Now we'll talk about why we study supernovae, Type Ia Supernovae, and why we study lens Type Ia Supernovae. So to give a background, I will just lay out these equations. So in cosmological, on cosmological scales, the evolution of the universe is governed by the first two equations. First is the Friedmann equation, which is h square. H square is the Hubble parameter, okay? And this is a general case where I am also including lambda, which is dark energy, and kappa, which is the curvature of the space. There have been a lot of observational evidences that the curvature of the space is zero. The universe that we live in, it has zero spatial curvature. But this is just a general Friedmann equation that I have considered here. A is the rate of expansion. It's the scale factor, the rate, so basically these are the 2 points, and we say that the universe is expanding. So first at time t is equal to t0, if the distance between these 2 points is a, or okay, the a is not the distance is the x, and at time t is equal to t1, the distance becomes something x1, for example. Then the relation between the x1 and x will be given by this equation. Just simply this, the scale factor is simply what is the scale factor, literally how the scale changes, okay? And the h is the well-known Hubble parameter. Rho here is the matter density of these three are constants, obviously. Rho is the matter density, or the density of the components that the universe is made of. So right now we say that we live in a matter and dark energy dominated epoch. Back in the evolution of universe, we had radiation epoch, we had matter dominated epoch, and now we are in matter and dark energy dominated epoch. So this rho gives the density of what matter, radiation, whatever the universe is made up of. So this equation, the matter content of the universe and how the expansion happens, okay? And this second equation is P is equal to omega rho. Rho is again the densities, and P is the pressure of different energies, and omega is the factor which relates the pressure and the rho terms. Okay, so now we have this A parameter which depends on time, obviously. It depends, we say that this thing is, the rate, the A is not constant, it's also changing. We live in a universe which is expanding. First is expanding, then it's accelerated expansion. So when we take A, dA by dt, it's give the expansion. It's expanding, okay? So this A depends on time, and we Taylor expand A. I will not do this here, but if you simply just Taylor expand A of t, and if you try to incorporate this A dot by A square term, which is h, and h0 is just the value of Hubble parameter in today's at current time, okay? And if you incorporate, then you get this thing, which is independent of cosmological models, okay? And you see I have introduced a parameter called q0 here, which is where q0 is A double dot upon A h square, which is called the deceleration parameter, which just gives what is the rate of change of Hubble's constant itself. Like it's the double derivative of A. Okay, the Hubble's parameter is the single derivative, and the deceleration parameter is the derivative of the Hubble's parameter. Okay, and this again might seem very unmotivated why we are doing this, but we need. Okay, so this is, I said this is the equation that governs the evolution of the universe, and now the theory has given this equation, right? And we need to vary the parameters, the h parameter, the rho parameter, the omega parameter. We will not consider these two parameters for now, but these four parameters, for example, h, q0, rho of I and omega of I. I is the number of components that the universe is made of: matter, radiation, dark energy, etc. So these are the most prominently, these parameters need to be there in that equation to figure out what is happening with our universe, right? And to solve for these equations or to find out the values of these equations, theory has given these parameters, theory has given this equation, but theory cannot tell you what are the values of these parameters in the world that we are living in. So if we need to find out what are the values of these parameters in our universe, we need to observe, we need to look around ourselves and see how and devise different methods by which we can find out the values of these parameters. If we successfully find out the values of these parameters in the universe that we are living in, we can use the Friedmann equation and the equation of state to figure out where our universe came from and where it is going to, right? And that is the ultimate motivation of cosmology, to know what is the origin of the universe and what is going to happen with it. And am I taking too much time, or I should continue it? Okay. So first thing is again standard candles, and okay, so just focus on this equation. We know this equation, right? The flux of any object is given as the luminosity of the body upon 4 by distance square, right? Just solve this equation for the distance and you will get that equation. And if you add in the formula of distance that you get from cosmology, you will get this relation, which is approximation again, because we are using the Taylor expansion that I show you. We are using the Taylor expansion of A in simplifying that formula, and you will get this relation. Focus on this relation: C upon h0, which is the Hubble's constant, today's Hubble parameter. C is the redshift, 1 plus 1 minus q0, which is the deceleration parameter, upon 1 C factor again. Now we know the DL. We can measure the DL because the original formula is L upon 4 pi L. The L is known because of the standardized luminosity of a supernova. We know L. The L is going to stay same for all cases of Type Ia supernova. The flux is measured by telescopes on the Earth, and the redshift Z. Okay, the luminosity and the flux is known, so we can find out DL from there. So the left hand side of the equation is known, DL, we know DL, and now coming to the right side, we know C, we know redshift because it is fairly easy to measure the redshift of any body, and the automated surveys they do it all the time, and we get the redshift value. The only unknown parameter, we know DL, we know redshift, we know C, and the only two unknown parameters are h0 and q0, and we can use this equation to find h0 and q0. We cannot do it simultaneously, but if we take the case where z is very very less, you can consider which are the objects which are closer to us. You can ignore the z in the second term, you can ignore the entire second term, and just focus on C, h0, z. And this is the Hubble's law. This is what Hubble did, and you might have seen that famous straight line plot that Hubble plotted. And this is the formula that Hubble used. He found out the distances of nearby objects, and he found out their redshift, and then from that we determined h0, value of Hubble's constant, and he gave this Hubble's law. This is the relation that the object is. He was of course very wrong in giving the value of Hubble's constant because he underestimated the value of distances. As you might know, the problem of finding distances or calculating the distances in astronomy is not a very simple task. So he did that mistake and got a very wrong value of Hubble's constant. But we have much more sophisticated instruments to figure out the distances, and using this relation we can find out Hubble's constant. If we consider high Z supernovae, like redshifts which are greater than 0.5 or 0.7, in those cases we have to consider the second term, and if we plug in the known h0 value, we can find out the q0 parameter. So this is one way of going towards it, and there are collaborations like high redshift supernova search team, Paul Mutter, Schmitz, and these people got 2011 Nobel Prize for their discovery of dark energy. So this was a paper by these two people. They work parallelly, they work independently, but at the same time thing. And both of their papers came out in 1999, which gave the dark energy, which predicted that the dark energy exists. The lambda parameter you see, right? You saw in the Friedman equation. We used to not consider it. We didn't know that something called dark energy exists back in before 1990, before these papers came out. But what these papers did is they studied luminosities of whatever number of supernovae, Type Ia supernovae that were present in their time. I think it was like 40-ish Type Ia supernovae were observed till then. We had data of around that many Type Ia supernovae, and we knew from the theory, we knew exact theory of how that runaway fusion reaction in Type Ia supernovae happens, and we had predicted that we should have this constant luminosity for all types of Type Ia supernovae. When these people studied the Type Ia supernovae, they realized that this is not really the case. You are not getting constant luminosity. The luminosity is changing with changing redshift. And then they did some modeling. It will take me some time to explain these graphs, but so I will sort of skip it. But you can see they put these constraints, these elongated things. They put these constraints. And if you can see these constants, this is the omega lambda, which is the density of dark energy. And they showed that this density of dark energy is not zero, it is more than zero. And then they proved that something exists there, and they named it dark energy in the due course of time. That something exists which is non-zero density, non-zero component density. This is the density of matter as in everything that we see, atoms, etc. And so they showed that this is non-zero. I mean, that this Type Ia supernovae played a very significant. They studied Type Ia supernovae and found this thing. So and today also these collaborations are working to find out more and more redshift, more and more supernovae, and figure out the constraints on what is the that parameter, what is the better constraints on that parameter. And the last thing is lensing. So we discussed Type Ia supernovae. We discussed the time delay in the this is time delay is again given by the same equation, and lensing, particularly lensing. The previous two applications that I discussed were general for any general Type Ia supernova. You don't need to have a lensing case to figure out previous two applications. But this third thing, you are utilizing the lensing parameter, which is time delay, and this thing comes out to be inversely proportional. The distance ratio comes out to be inversely proportional to the Hubble's constant, and if you plug it there, we know redshift, we know time delay because we are observing the time delay in the images, and the Fermat potential we know by modeling the lens system. And there are many efficient ways to model a lens system. So we know these quantities, and it's just the inversion and finding out the LCD. So you might have heard this discussion about Hubble tension, and people are not able to reach a constant value of Hubble's parameter, and you might wonder why is it so important to know the Hubble's parameter. It is important because a lot of things, the most important equation starts from the Hubble's parameter. So I think that's about the application, why we need to study it, and slide overview of what I am doing. What I am doing is, so this is the LSST, this is the artistic depiction of LSST, which is Vera-Rubin Observatory Legacy Server Space and Time. So it's getting built in Chile right now, and it will complete its, it will be working around 2025. And what I am doing is I am trying to set up a pipeline which finds out the cases of Type Ia lens supernovae. So this telescope will survey the sky throughout 10 years. Each night it will survey the sky, and it will have extensive amount of data, and from that data my work is to set up a pipeline which will extract the lens cases of Type Ia supernovae. And I have been working at ISCA, this is a very pretty campus of Aiba, and I will go there again in my summer. So I really hope you will capture some of the essence of